All right, good evening, everyone. So I think I'm just going to quickly go through Module 7 and maybe highlight, because there are a few mistakes here and there from the textbook in terms of the diagrams. I just want to quickly go through that. So you guys will see Module 7 is actually just kind of more on Chapter 6, really. So instead of making use of diode rectification, we make use of SCRs. Now, SCRs allow us to do quite a few things. So, for instance, we can now conduct only part of our waveform. So, in the case of our half wave rectification, we can actually decide, listen, we want to be able to control our average voltage. That's one way of doing it, is by means of SCRs. As you can see there, so by adjusting when we fire our gate signal, you can do that. Right, so SCRs open up a world of other things that we can do. So for instance, what we can do now is, so if you were to have a DC motor, for instance, so if you want to control that DC motor speed, you can now use an SCR to do so. You can do light dimmer circuits using SCRs. You can do heater control. Quite a few things you can do with SCRs in both DC and AC applications. All right, so we're also going to take a look at a few variations as well. So the other thing that we have here, so basically a component that will allow us to do full wave control on so in this case, full wave AC control. So if we use a component called a triac, now a triac is essentially two SCRs connected in parallel but counterpolar to one another, and they will then share a gate, but so they will look something like this. So it's essentially equivalent to that. So we can use triacs and quadracs for full wave control. A quadrac actually includes a diode somewhere in the mix as well. I think it's on the gate signal. I'm not too sure. I can't remember. Oh no, it's not a diode. It's a diac. The diac is a bidirectional diode as such. But anyways, that's a quadrac that will look something like that. But in any case, that will allow you to do full wave control. Okay, so we have, so obviously you need to trigger an SCR at a specific point in time. Now, for some reason in this subject, we mainly look at a very rudimentary trigger circuits. So in reality, we don't actually use trigger circuits like this anymore because they're very inefficient in terms of power usage. And that is just a simple RC circuit. So the thing that's left out in this drawing, though, is maybe a load. Otherwise, you're just going to have a dead short there with your SCR. But essentially what you have is you basically forming an RC circuit there with a time constant, with its own time constant. And this being AC as well, you're also going to have a phase shift. So by adjusting the resistance there, you will actually adjust when you will have a gate pulse applied to your SCR to put it into conduction. All right. And I'm pretty sure you guys know how an SCR works as well. So maybe just quickly explain here. So for an SCR, basically if it's forward biased and you have a gate pulse applied, your SCR will continue to conduct as long as it stays forward biased, but the gate pulse can be removed. You don't need a gate pulse or a signal applied to your gate consistently. But let's say for some reason your SCR gets reversed biased, that also cancels the current through it. right, will stop conducting. Or if you interrupt the current flowing through it, then it will also stop conducting until the next gate pulse. All right, and then we get to the concept of the delay angle and conduction angle. So delay angle, that's the point at which the SCR is triggered. So that's the part of your waveform that you have no conduction. That's your delay angle. Conduction angle, on the other hand, that is the part of your waveform that is conducted. That's your conduction angle. So yeah, so as you guys can see, we have half wave control and full wave control. So the half wave control is not demonstrated very well here. It should actually be just that. And then for full wave control, yeah, so you actually get full wave AC and full wave DC control. So this here is full wave AC control. It here. So we're effectively changing the RMS voltage or RMS current to control, let's say, the brightness of a light bulb in your house. Okay, so your conduction angle is basically going to determine the output to your load. So it means that the smaller the delay angle, the more of your input waveform will be available, meaning you're going to have a higher average voltage applied to your load. And the larger that delay angle, the less of your input waveform is then available to your load. Right, then that means you're going to have a lower average voltage. Right, so there are some circuit layouts. So you guys will recognize that this is very similar to what we had in chapter 6. So the first one that we do have here is the half wave rectifier. Yeah, so for some reason, I think this is from the textbook, so the diagrams are a bit weird. But in any case, the voltage across your load is then going to look like that. And then obviously the voltage across the SCR is then going to be this. So for some reason, they don't include the negative blocking voltage that's being blocked there as well. So that's the so essentially, when you add the voltage across the SCR and the voltage across your load, they need to give you your input waveform again. And then you also have full wave SCR control. I think what's demonstrated here is full wave AC control with this diagram, but we'll take a look at a few circuit examples as well in a moment. Now then, again, we can actually classify SCR circuits as half-wave DC control or half-wave. I don't think there is half-wave AC control, but yeah, half-wave DC, full-wave DC, and full-wave AC control. Now, pretty much the only example of half-wave DC control would be essentially a half-wave rectifier making use of an SCR. So yeah, so essentially you have your load in series with an SCR, and you have a trigger circuit. And depending on where you set your conduction angle, that's then going to give you an output. It's pretty much going to look like that. Pretty much like half-wave rectifier with a diode, but you can adjust when this diode essentially conducts. Full wave DC control, that's essentially just a full wave rectifier making use of SCR. So the example that we have here is a center tap transformer configuration. You can also do a bridge rectifier configuration as well. The bridge rectifier configuration, though, has a few advantages to it. So, for instance, if you make all four of your switches SCRs, then you can actually reverse the direction of conduction as well. Then you can actually have a circuit that you can use to change the direction of rotation on a motor if you wish to do so. But anyways, full wave DC control, as you guys can see, essentially full wave rectifier, 2 SCRs, and you are essentially each portion of your waveform you now can control when conduction takes place. full wave DC control, bridge circuit. So you can have either all 4 of your diodes replaced by SCRs or just 2. It's going to have essentially the same effect. If you just replace 2 of them with SCRs, yeah, so you can actually then essentially just do conduction between, yeah, so your firing angle can be anywhere between 0 and 180 degrees, whereby a firing angle or delay angle of 180 degrees will give you a zero output. If you were to replace all 4 with SCRs, just as a curiosity here, then you can actually change the polarity of the output voltage. Full wave AC control. So for full wave AC control, so you guys will see it almost looks like a rectifier bridge. In fact, it is a rectifier bridge with 1 SCR. So essentially, you are changing your voltage here to DC, but you are essentially chopping up your output voltage. Right, so that's the voltage that you're going to see across your load. Right, so that's one way of doing it. That's making use of 1 SCR. The other method makes use of a triac or that parallel SCR configuration I showed you guys earlier. Then we have half wave DC control again. So here we have a bit more of a detailed trigger circuit. So this is our trigger circuit that we have here. So take note, we also have an RC circuit configuration here. That will give you a time constant and phase shift at which you can adjust when the SCR is triggered. And also take note, we have a Zener diode. Now, essentially what we're trying to do here is we want a sort of a square wave pulse applied to our SCR instead of a part of our waveform. So yeah, so that Zener diode is going to clamp the voltage applied to the gate to a fixed level. Right, so also if you apply too high a voltage on your SCR's gate, you can also damage it. Okay, but I'm pretty sure the circuit, I'm not too sure on the correctness of the circuit. I haven't been able to verify if this is wrong or not. But I think the next one, yeah, the next one is actually incorrect. Okay, and I think you guys can probably see why. Ignore all the other stuff here, but you guys can probably recognize the rectifier there. And the thing that's wrong here is that our transformer is also connected incorrectly. A transformer needs to be connected there. That can be, let me maybe, I don't have white. Okay, so that line needs to come out. Our DC load here is also connected incorrectly. Shouldn't be connected there. In fact, your DC load needs to be connected to this corner here where the transformer is connected incorrectly. So that's how that should be connected. Then your circuit is correct. Right, so this is a mistake in the textbook. I actually, I shouldn't actually have left that textbook at the campus. But yeah, I used to have an older N5 textbook that had the correct circuits in it. So yeah, so that's actually a mistake from the new textbook that has that. But in any case, there's your correction. So that's your DC load. Then again, you have your trigger circuit set up here. Again, what these diodes, D3 and D4, what they're going to ensure is that your SCRs, yeah, so they're going to clamp the voltage down to a certain level. These diodes can also be Zener diodes. So yeah, so that's also something to consider there. And yeah, again, there's your output waveform, but this is for the, then you have the whole trigger circuit. This is making use of 2 SCRs in this case. Full wave AC control done with a lamp. So this would be your typical light dimmer circuit. This is actually an inductor that's put in the circuit there. But yeah, so again, this combination, basically this combination here, that's going to give you your RC time constant and phase shift to trigger your triac here at the correct time. So essentially this, so the triac and diac combination here is actually what we would call a quadrac. And again, waveform output is going to look something like that. So hope you guys can see we can control the brightness. So this is actually not for an LED, by the way. Going to struggle a little bit with an LED lamp using this circuit. This is for incandescent light bulbs. Right. You can control the brightness then this manner by controlling your RMS voltage. With LEDs, so LEDs is a bit more troublesome. Just as a curiosity here, just to show you guys. So with an LED bulb, you have a fixed voltage drop, right? So that's your V forward. Can't change that. That's not going to do anything. So you're kind of stuck with that voltage across your LED. Now, essentially what you need to do with an LED is you need to find a way to change the current flowing through it. Right, so there are a few ways that you can do that. You can do that either by inserting a resistor in series with the LED, an adjustable resistor, which is not ideal because it wastes a lot of power that way. The other way is by changing the average voltage. That's going to change the average current. So you're not going to change the forward voltage drop of the LED, but you will be able to have control over the average current flowing through it, and thus you can control the brightness of the LED in that manner. Right, so there are a few ways to do it. The problem is the circuit that we have here is more focused on changing the voltage level and not the current level. So you are going to so you are going to struggle a little bit with the circuit to with the LED lamp to adjust the brightness. Righty. Okay, so we're kind of flying through chapter 7 here, which was what I wanted to do. Initially, I wanted to give you guys this as a self-study, but I think I'm going to not do that, and then we can actually look at chapter 8 tonight as well as next week. Okay, so then we also so a little bit of an introductory into control systems. So you guys are going to see this again in industrials in 6. Actually, not that difficult to, or rather, the level at which you guys go into this is luckily not too complex. But in any case, to contrast open loop and closed loop systems with one another. So the simplest explanation for an open loop system is where you have a system that there is no feedback to adjust your output. And then in a closed loop system, that would be a system where you have feedback that will allow you to compare that feedback output to your input and see, so usually your input is going to be the value that you want to reach. And if the input and your feedback differs from one another, then obviously your output needs to be adjusted. Right, so in open loop systems, you don't have that feedback. So this is also sort of an introduction to chapter 8 as well, if you think carefully about it, because the only way you're going to get feedback is by means of a sensor or a transducer, which is what we're going to take a look at in chapter 8. Right, so in an open loop system, so for instance, in an open loop system, or rather an example of one, is where you don't have any level measurement in a tank that's being filled. So that could be filled with fuel or filled with water via a pump. And the only feedback in this case would be you as person. You standing there looking at the water tank, wait till the level is where it needs to be, and then switching off the pump. Right, so that is yeah, so then you as person then act as the feedback there, which is not ideal because ideally we want the process to be automated. So in a closed loop system, now a closed loop system is basically a system where you make use of feedback. So usually to achieve that feedback, we usually measure the output. Now usually, yeah, so for most cases, your output here is going to be of a different unit than, let's say, or your input. So in this case, our input is a reference voltage. Our output could be something like rotational speed, it could be water level, could be displacement, anything of that nature. So physical uh, quantity. We can then use a sensor to measure it. So the sensor is actually going to form part of our feedback network. And part of the feedback network is also going to be amplifiers and signal processors that will then change that value that we measure with our sensor into a voltage that we can feed back to our reference input. And then the feedback voltage is then going to be subtracted from the reference input to give you an error. And yeah, so based on the value of the error, your controller the necessary adjustments to your process, and then it will output again and will be measured again. So this will continuously correct itself till the error is 0. Right. And when the error signal is 0, that's basically when your feedback and your reference voltage is equal to one another. Okay. And guys, yeah, that is chapter 7. So we've done it in 30 minutes. It was actually quite quick. Right. So I'm also going to start now with chapter 8, as it does have quite a bit of theory as well as calculations to get through. I don't know if I'm going to be able tonight to do an example, but let's see how far we get. Okay, so chapter 8 is transducers. So if we take a look at what a transducer is, it's pretty much a device that will convert one form of energy into another form of energy. So that's usually going to be, so for us as, in electrical engineering, essentially what we want to do is we want to take, let's say, something like temperature or force or displacement and change that into some form of electrical or electronic value that we can measure. Right, so we can divide transducers into two categories, mechanical and electrical. Now our main focus is going to be on electrical transducers, and electrical transducers will give you an electrical signal, usually in the form of a voltage or current that is then calibrated in terms of the change that it's measuring. So for instance, um, you're going to have, so let's say you have a thermistor that will give you, or rather not a thermistor, let's say, oh my goodness, what's the thing? A thermocouple. A thermocouple that will give you 10 millivolts per degree Celsius in temperature change. So that is, yeah, so that's basically a conversion from degrees Celsius to voltage. And then we can further divide electrical transducers into two further groups. So we're going to have passive transducers and active transducers. Now, passive transducers are going to need an external power supply or external excitation supply. And they are basically, yeah, so basically how passive transducers work is that they going to produce a variation in some electrical parameter, usually in the form of resistance or inductance or capacitance, that we can then measure the voltage over that component, the voltage or current for that component, and then yeah, that's pretty much how that functions. In the case of active transducers, they will generate their own current and voltage. So examples of this would be things like thermocouples and solar cells. And they do not require any external excitation supply to to operate. Okay, so the three major elements in a measurement system or measuring system would be your input device. So your input device in this case is going to be your transducer. And yeah, so that's usually going to measure or receive a quantity that's usually non-electrical. Then your second major element here would be your process device. Our process device would usually be something like an amplifier or any form of signal modifying device. So amplifier can be a digital to analog converter, analog to digital converter, or it can even be something a differentiator, a filter circuit, or anything that you do to change the signal from your input device. And you guys will see a lot of the times you will have to implement an amplifier, especially amplifiers and filters, to get rid of noise, firstly, and then secondly, to amplify your input signal as well, because a lot of the times the input signal is or the signal from your sensor is actually quite small. And then lastly, you have your output device. Yeah, so that's also why we need the process devices, basically to get your sensor quantity to an acceptable quality um, for the output device, or into an acceptable format. Right, so your output device could be something like a digital control system, for instance, right? So a digital control system is not going to be very receptible to an analog voltage. So you will have to make your signal a digital signal, for instance. So your process device in that case could be something like a Schmidt trigger, for instance. Okay, so there's some criteria that we also need to look at when selecting a transducer. First off, we need to determine the physical quantity that we want to measure. So basically, are you measuring temperature? Um, are you measuring displacement? Are you measuring force? Are you measuring um, flow rate? There's a whole bunch of stuff that you can go look at. Then Then the next part is you need to decide which transducer principle is best suited to measure this quantity. Right, so you guys will see in this chapter as well, there are actually quite a few transducers. So let's just take displacement, for instance. There are quite a few transducers that can measure displacement, but some of the transducers are really good at measuring change in displacement versus an absolute displacement. Right, so absolute displacement meaning you just detecting the distance that an object is away from you, but you're not concerned about a change in distance. Whereby some transducers will only give you an output if there's a change in distance. So if the distance doesn't change, it's not going to produce any output. Right. So you need to decide what you want to do there. And then also on that second point is what is the kind of displacement that you have? So is it very big displacements or is it very small? For instance, you're not going to use an ultrasonic sensor for very tiny displacements. Ultrasonic sensors are very good with medium, okay, yeah, I can say maybe medium displacements, whereby something like, oh my goodness, what's the thing called? A strain gauge is very good at measuring very, very small, minute displacements. Right, so you have to know what you're measuring and what kind of principle you're measuring on there. I think your third your third criteria that you need to look at is the level of accuracy that you need for that measurement. I might also want to add precision there as well. So, for instance, something that's going to operate in a military application is obviously going to require a much higher level of accuracy and precision than something that's going to be used in a domestic sense, so in your house, for instance. So yeah, so there are quite a few considerations to take account of here. And there are quite a few factors that will affect your accuracy as well. So you'll have physical conditions. So your physical conditions will be things like your electrical mechanical connections. So basically, if you have plug points or joints that need to be made between your sensors and your interface circuitry, the mounting of your sensors. So all of those things, yeah. So mounting of your sensor. So if your sensor has a very flimsy mounting, it's going to give you noisy readings. If you have a mounting that might be too stiff, that can also cause issues. Then you also have some environmental conditions as well that you need to take into account. That would be things like shock and vibration, temperature, corrosion, that kind of stuff. Fundamental parameters. So this would be basically how are you going to excite your transducer. Yeah, so the excitation type basically. So are you going to use a passive or active transducer? Also need to consider the range of measurements in the case of accuracy as well. So for instance, you might have a transducer that may only be able to measure distances between, let's say, 1 and 5 centimeters, but your application requires that you measure, let's say, 2 to 10 centimeters. So the transducer that you then have there is not going to work for that particular application. So if you're going to have displacement above 5 centimeters, you are just going to read the same voltage throughout up until 10 centimeters of displacement and beyond. So your system might break and you won't know it. Then for other things that will also affect your accuracy would be uh, adaptation to associated equipment. So meaning things like impedance matching and zero balance provisions that need to be made. So yeah, so this is a particularly true when you have with your process device. So if let's say your sensor has a low output impedance, then you also need to ensure that the amplifier that you're going to use or the circuit that you're going to use to interface that sensor to your output device also will have a low input impedance. Right. So that is if your sensor has a low output impedance. And if it had a high output impedance, then obviously your process device also needs to have then a high input impedance. Transducer characteristics can also affect your accuracy, and this is usually in the form of things like frequency response, resolution, hysteresis, nonlinearity. So yes, actually quite a few things there as well. Okay, and then you also have different types of passive transducers. Now, I'm not going to read through all of them, but what I would say is for the subject in terms of calculation examples, we are going to take a look at the strain gauge. We're also going to take a look at the thermistor. And yeah, we're actually going to take a look at the photocells or photoconductive cells as well. And for capacitors, not really going to do any calculations here, but it's something you guys can take note of. Inductive passive transducers, we are going to take a look at both these, the differential transformer, more specifically the linear variable differential transformer, so the LVDT. And we're also going to take a look at the magnetostrict. Oh no, actually not for this subject. It's actually N6, that one. So we're not going to take a look at that one. Then passive transducers, voltage and current. So you have your photoemissive cell, photomultiplier tube. This is, yeah, so photomultiplier tube is actually something that you guys are going to see in N6 again. Actually do calculations with that thing. It's actually a very interesting device. But not really being used anymore. Let's just put it that way. Then your active transducers, you have the thermocouple. So this is actually a very common one. Piezoelectric crystals. Yeah, so usually used to measure things like forces, pressures, and displacements. And then also your photovoltaic cells or solar cells. So yeah, so that's yeah. So solar cells, they're not just used to generate power. You can also do light measurements with them as well. Okay. Right, so I think the first few transducers that we are going to take a look at are going to be all resistive transducers, and basically we're also going to take a look at some applications here. So I'm going to quickly go through some of them. Okay, so the first one that we're going to take a look at is the strain gauge. Now, I think what I'm going to do is I'm going to show you guys what this will look like as well. It's actually quite an important little device. I'll share my screen in a moment. Right, so basically what the strain gauge operates on. Well, if we take a look at what resistive transducers do in general is they will change resistance when they are subjected to some form of physical change. And that's going to depend on things like stress, so basically deformation, some way or another. So that's where the pressure comes in as well as displacement, light, temperature, so quite a few things. And again, resistive transducers are all passive transducers. So they are going to require some form of voltage to, or some form of power source to have them work correctly. Right, so the first one that we have here is the strain gauge. Now, strain gauge, so this will depend on the dimensions or dimensional changes of a conductor that it's made from. Right, so I don't think I have the materials from which these strain gauges are built in the slides, but I think it is in the textbook. But it is it's quite an interesting conductor. It's actually highly resistive, but very sensitive to dimensional changes. So if you change its length or its width in some way or another, um, it actually gives you quite a drastic change in resistance. Yeah, so you basically, a strain gauge will have its resistance changed when it's subject to elongation or compression due to external stress or pressure. And we mainly use strain gauges to measure things like force, torque, or displacement. And displacement, when I speak of displacement here, I'm not talking about meters and meters of displacement. It's very small displacements, anything from like maybe a few nanometers up to maybe a millimeter or two. And we usually, usually they're used in a Wheatstone bridge configuration as well. So if we take a look at an example here, so typically you'll have a compensation gauge and an active gauge. Now the active gauge is the one that we're actually measuring across. This compensation gauge we can actually use, that can actually be just to balance the bridge in the beginning before we measure anything. So this is the gauge that's going to be experiencing stresses in whichever direction. But you can also use the Wheatstone bridge to, so if you were to make all four of these strain gauges, then you can actually measure the direction of displacement as well. Okay, so so there are a few things that we need to know about strain gauges here. Now, first off, how sensitive a strain gauge is called the gauge factor. And gauge factor is effectively the unit change in resistance per unit change in dimensions. Or you can also say the ratio of resistance change to ratio of dimensional change. And yeah, so the delta R is then obviously going to be the change in your gauge resistance. R is going to be your gauge's standard resistance, so basically the resistance that it will have when it's not under stress. And then delta L is going to be the change in length of your strain gauge, and L is going to be your normal or nominal length of your strain gauge. And we can go and calculate the strain, or rather the strain is expressed as delta L over L. And that's going to change our gauge factor equation then to look something like that. And yeah, so basically delta R is going to be dependent on this little relationship of ours, whereby, or rather the relationship between resistance and the and the dimensions of your material, so length, area, and its resistivity. And yeah, and stress is the applied force per unit area. Strain is the elongation of the stressed material per unit length. And then there's a very important law here, which is Hooke's law, which states the relationship between stress and strain. So S here is stress, and E here is what we call Young's modulus, or the modulus of elasticity. That's then going to be kilograms per centimeter squared. The stress is also kilograms per centimeter squared. And yeah, so that will also give us the strain. So yeah, so this here is also equal to that. Right. Cool. And I think we can take a look at an example. There's an exercise in the textbook as well as an example. But quick, I just want to show you guys the materials that strain gauges are made from. There's actually quite a list in the textbook. It does get asked from time to time in the exams. So yeah, so just wanted to show you guys. So those are the types of materials that strain gauges are made from. Okay, cool. Don't need everything highlighted. Whatever. But yeah, here are the materials. And then in example 1, yeah, so example 1 is pretty much a very typical question that you guys can expect on strain gauges. All right, so I'm going to take a look at the exercise in the text. I think there's 1 or 2 exercises here. Just, okay, cool. There's no scroll bar here on the right. That's nice. Okay, there's a bar, but there's no thing to, there's the thing that I can select. I just want to go to the end of this chapter. Okay, so I'm going to let me scroll again using the scroll bar there. Just do this, as this chapter is quite extensive. Right, exercise 8.2. Okay, so 8.1, I have no idea. I can't remember what that was, but 8.2, yeah, it's actually the exercise that we're more interested in. It's actually the exercise with the real exercises in it. Put it that way. Okay, so let's take a look at this number 8.2.1. Okay, so yeah, so this is actually a pretty straightforward one. So we're given the gauge factor, which is K. We're given the stress applied, which is S, and we're also given the modulus of elasticity, E. Right, so the strain, that's going to be S over E. In this case, that's going to be 1155 over 2.1 times 10 to the 6. That's going to give you 0.55 times 10 to the minus 3. And we can actually now go and calculate. Yeah, so we're essentially going to calculate the fraction of resistance change. We don't have enough information to calculate the actual change in resistance. So, well, I'm going to calculate the percentage of resistance change essentially. So K, that's then equal to delta R over R over that. So delta R over R is equal to K multiplied by the strain. That's going to be 1.5 times 0.55 times 10 to the minus 3. So this can be 0.825 Becomes 10 to the minus 3. Or you can write it down as, if we multiply this with 100, I think, would that be correct to multiply it with 100? I don't think so. Will it be? I think no, it's fine. Multiply this with 100, it becomes, yeah, so multiplied by 100, that will then become 0.825, 10 to the minus 1, which is then 8.25% change. Is it? No, I'm lying. It's 0.08. 0.0825% change. All right, so that's how you go about with the strain gauges. That's a pretty good typical question for strain gauge. All right, any questions from you guys? I think we pretty much just going to continue from here on next week.